What's going on, everybody? This is Mr. Diamond, and today we're going to be doing, these notes are so short, I don't really feel like it's actually worth it to do the PowerPoint for them. We're going to be doing a little bit of notes on labeling. Let me make sure my thing's on screen. Of labeling, I hope it spelled that correctly. Labeling is one of the things that always autocorrects for me. Forces, labeling forces. And this is because we're going to be talking about a bunch of forces. And not just like, oh, we'll be like discussing them abstractly. Like, we'll be using a whole bunch of different forces in a lot of our problems. So to represent that, we're going to use what are called free body diagrams. We're going to treat each of the things that we're caring about as though they are a free body. They're not inhibited or attached to anything. So, for example, your head is attached to your neck and is attached to your body and is connected by tissues and muscles and bones and things like that. But if you were doing a problem where you were calculating the forces involved in a head, like, for example, the car crash, or one of the examples that's going to be in one of the worksheets coming up, we're going to treat the head as though it is a free body. We're going to pretend that it's not actually bound down by that, and it's going to act in response to whatever forces it has without those weird connections, things like that. It just makes things a lot easier. And they show all forces you try to do the magnitude. That one's a little tough. And you definitely show the direction as vectors on it. So let's say, for example, we've got, I've got a cube. And my cube is just resting on the ground. We're gonna have it just resting on some flat ground. Got a little bit of dirt, a little bit of grass going around it. This is very important to the example, I promise. It's not actually important. So we've got it resting on some grass. To draw this as a free body diagram, we're going to use it as a square. Now, that's not because it's a cube. We usually just represent these things as squares. You can do it this small, but because I want it to be very clear what we're actually using, I'm gonna blow it up a little bit. So we've got our square. Now let's go ahead and think about all of the forces that are acting on this cube. So currently, if it's just sitting on the grass, there's probably not any horizontal forces acting upon it. But if it's on a planet, which it probably is because there's grass. See, told you the grass is important. We've got gravity. So we're going to do F gravity. That's going to be pulling it downwards. Now, as we're going to talk about, and we talked about a little bit in Newton's third law, but we'll go into more detail later, there is another force that actually is going to be directed in the upward direction. And that's the force of, so this is the downwards force is the force of the weight of this box sitting on the ground. This is the weight of the ground supporting, or the force of the ground supporting the box. We'll talk about this more later. This is called the normal force. No R-M-A-L, normal force. And that is, for the purposes of this, all of the forces acting upon that box. So it's pretty straightforward. I'm going to do a couple other examples of things that will, just to make sure that we can practice. So first, let's have a box suspended by a string. And for each one of these, I do recommend you pause the video and kind of try this yourself. So we've got box on a string. So if I move this over here, that's my example of what the picture is. I've got my box right here. So it's going to have gravity pulling it down. And there's no normal force supporting it this time. What's supporting it is that string. And that string is actually being supported because of tension, which I'm sure is something that none of you guys know anything about. So the force of tension is actually holding that in place. I'm going to zoom in a little bit more so you can see a little bit better. So we have normal force going up in this one, gravity going down in this one. We've got gravity going down here, but it's the force of tension that's actually supporting it in this case. It's not a normal force supporting it in this example. Okay, next let's do, what about somebody pushing a box? So pushing a box. So I've got my box. It's on flat ground. And we'll say on rough floor. We're pushing the box on a rough floor. And so I've got my person standing here. He's kind of leaning into it. His arms are curved in a very weird direction because I am bad at drawing. And so he is pushing that box. So we've got for our free body diagram, we're going to go ahead and draw our square shape. This is our free body. It's on the ground. It's on the earth. On the earth, it's got a gravitational pull. On the ground, if it's not floating away or moving upwards, it's got the normal force. And this person is pushing it forward, but it specified that it was on rough ground. So if it's on rough ground, there has to be something kind of pulling backwards at it and making it harder to move. So we're going to do that. Notice I make it lower. I just tend to do that when we're talking about this specific force. It's the force of friction. Friction is going to make it harder for you to push that. It says it's on a rough floor, so there's going to be friction making it so that box doesn't move as easily going across there. So all of these forces are acting on this box. Okay, what else do we got? Let me move my camera so I got a little bit more space. What about a box that is just falling? So I've got my beautiful, beautiful cube, and it's just falling down. It's not attached to anything. Well, the only thing that would be acting on it then, if we ignore air resistance, would be force of gravity. The force of gravity is the only thing impacting that object while it's falling through the air. If there was air resistance, we would say the air resistance is going this direction, so it's air resistance or drag. But in most of the problems we're going to do, we're going to be ignoring that, so you don't really need to worry about the air resistance or drag. Okay, for the final example, I'm going to have a box that is on a slope, on an inclined plane. This is where things get a little bit weirder. So I've got my box. It's positioned right here. And it's stationary. It's still on this inclined plane. So box resting on plane. And we're going to talk about inclined planes quite a bit later in this chapter when we get to the more complicated examples, but let's go ahead and think about all the things that are acting on it. Well, gravity is, your instinct might be to do gravity this way, but remember, gravity goes straight down to the center of the Earth, the gravitational center of whatever planet you're on. So gravity is actually going to go this direction. It's actually going to be at an angle, and that angle is actually going to be theta of whatever the slope is. So that's the angle gravity is going to make down there. We'll go into more detail about this later, so don't worry about memorizing that. You don't need to write that. Just it's going to go straight downwards. And the normal force, remember, it works perpendicular to the surface. So normal force isn't actually going straight up this time. The normal force is actually directed in this direction. It's going to go off at an angle here. And then something must be keeping this box in place, because otherwise it wouldn't be resting, it would be falling. If there was no friction or anything like that, it would be sliding down the slope. So since something is keeping it up, there must be something pulling it this direction, and that must be friction. The force of friction must be keeping it in place there. Now, what if instead we have somebody pushing that box? So let me click over and make sure. Okay, no. My camera is focused on all this. Good, good, good. Okay. Okay, so I've got my box again, but now I'm going to have my horribly drawn person. He is pushing with his absurdly long arms this box up the slope. So I've got my box, and I'm going to draw it. We'll draw it on another slope down here, actually. I think that'll be easier. So I've got my slope, and now this guy is pushing the box up the slope. So gravity will still go down. Normal force will still go up at an angle. And then our push, force of the push is going to go this direction. We're still going to have friction, but it's not going to act at nearly the same amount as it was before. It is still going to be directed this way because you're not just going to be able to willy-nilly push it up there, but most of the difficulty of pushing up the slope is going to come from the fact that gravity is pointing downwards, not actually the friction. So all of these are free body diagrams, and remember, all of these are vectors. So because they're vectors, you can use all of the rules from the last chapters about adding them. You can do tail to tip. You can do any of the other methods that we talked about, or any other the techniques using trig and anything like that to solve problems related to these vectors. So this is kind of a little bit of an introduction thing. It'll help you prepare for some of the stuff we're going to be doing later in this chapter. I hope that makes sense. If you have any questions, please send me an email or comment them. Let me know if I can help in any way. In the meantime, though, this is Mr. Diamond signing off. Have a good rest of your day, everybody.